Okay. So this is the badge that we made. I have one here, which I can show you later if you're interested. The code is open source. It's available on GitHub if you'd like to take a look. So I will give you a bit of an overview here, and if you want to go download the code, if you want to send us a pull request because you have something cool you'd like to add, feel free to do that. So what are we building today? What we're looking at is how to write the software for a PCB badge that has an LCD screen. This one is 2.8 inch, 320 by 240, so a little smaller than the conference badge for this conference. It has some buttons for interactivity. It has some blinky LEDs because we still have to blink. And it has the shitty add-on port for powering shitty add-ons, of course. So today what I'll be doing is talking about the hardware and dev toolchain that we used a little bit. And then I'll talk about the outline of the code, the shell, which is the part that runs all the games and apps that are on the badge. I'll talk a little bit about performance considerations that we had, the display, scrolling, some questions about Bluetooth, and the use of the serial port. So the first lesson that we had was that, software for badges, it's not that quick to write. It takes time. So if you're going to be developing a badge, make sure you've got some kind of hardware that you can prototype on. You can create an early prototype using off-the-shelf dev boards and proto boards, which is what we did. That's my glorious soldering attempt there. Don't look at that too closely. You can create a board without the artwork if you're not ready. You can reuse hardware. So for next year's badge, my plan is to reuse the GPIO pins that are on the shitty add-on port to add a couple of extra buttons because we didn't have enough buttons on this one. So giving something away there, sorry. So what we used for our hardware prototype was an Adafruit ESP32 feather board. And we got a display also from Adafruit. The code itself was written in C, C++-ish. And why did we do that? Not because we wanted a hard challenge. We wrote it in C because what I really wanted was to get the performance. I wanted the animation to be pretty smooth. I wanted it to feel like you were playing an arcade game with dedicated hardware. Also, using C means that I can use the ESP32 specific calls much more easily. It let me do things like use two processors on the ESP32, which is difficult to do with some of the other options. It let me get access to some of the other things like the Hall effect sensor and stuff like that, which I'll talk about more in a bit. So the tool chain we used. I used Arduino. It's the easiest way to get started. It's not what I ended up using for the whole thing, but it's a good way to get started. I supplemented that with the processor-specific code when I needed to from Espressit. I use GitHub for sharing the code with my co-conspirator on the badge, and also for sharing the code once I was ready to publish it. For actually doing the editing of the code, I didn't really like the Arduino IDE so much for just doing the text editing. I'm used to something a bit more powerful. I used Sublime Text. You can also use Visual Studio Code or Emacs or Vim or pretty much anything. But choose the editor you're comfortable with. Don't feel like you have to use the Arduino editor just because you're writing Arduino. And when you're flashing badges, Arduino has this nice thing where you can ask it to print out the command line, and that's how you flash multiple badges very quickly. You don't have to actually do it through the IDE. So that was the tool chain. So let's look a little bit about the shell. So the shell that we used, as I said, has the splash screen, which you see when you first power the badge on, and that just tells you, hey, here are the buttons. The lesson that we should have done was we should have also put the software version number on the splash screen. That would have meant that when we turned a badge on, we could tell if we needed to reflash it or not. So if you're writing one of these things, highly recommended, add the software version number. Don't do what we did. So this has a greeting. It gives you a list of menu choices. So you can play the Lander game. You can play Commander. You can adjust some settings. You can look at your friends who you might have shared scores with on Bluetooth. You can see the credits and so on. If you've got a game selected, it tells you your score. I was at 32 games, 116. That was why I stopped at this point, because this was just pretty much perfect. It shows you the battery level as well. We're using a great big LiPo battery, and you have to be careful of those things. You want to make sure that you don't completely flatten it. So it's good to keep track of the level. So we show that. The other thing that the shell does is it drives the actual game itself. So it drives the app, which is the game. So looking at that, here's what the app interface looks like, and here's where it looks a little like school, whatever. Okay, so the app is the basic thing that we used for implementing the Lunar Lander game. The Friends app, where you use Bluetooth to find other people who may have played the game. The Commander game, greatly underrated, the Commander game, and the Settings app as well. Here's what you have to implement if you're going to go ahead and build one of these apps for this badge. There's a couple of things you have to override. You need to override the start method. And that takes the current time and a color map. I'll show you the color map later. It's not like the palette on the Hackaday badge. This is much more naive because we're doing vector graphics, not raster graphics on here. You have to actually do something, which is what update is complete does. So it updates the screen and returns true if you're done. That gets called periodically, and the app controls how frequently that gets called. We have a way of figuring out if the app is actually running or not, and of course, every app needs to have a name. So, the other thing though, if you want to do something a little more interesting, is you might also want to override the blink action, where you can blink things that are on the screen if you want to. So on the screen for our game, the landing zones blink on and off periodically. You also want to if you want to interact with buttons, you need to override this button action thing. You don't have to. You can write something that doesn't interact at all. It maybe just shows a video and then stops. That would be fine. If it's a game, you probably want to be able to reset statistics. You want to be able to return the number of games that were won, played, and what the current score is. One of the things when you look at the Blinky example for Arduino, and a lot of the early examples that come with an Arduino, is that it uses this delay call. And that's not a great idea if you want to have animation that runs smoothly. So, if you use delay and you might, at this step, you do a lot of work. You know, you might do, say, 30 milliseconds of work, and then the next time you do 5 milliseconds, then maybe you do, 200 milliseconds of work. What you'll notice if you've got a 30 millisecond delay in there is that the animation looks really jumpy. It pauses, and then it goes really fast for a few frames, then it slows down again. And so what we do instead is we spin loop. And I'll show you what the code looks like for that. The other thing that delay does is it locks out the polling for button presses. And so if you're polling for button presses, which is the approach I took here, you really want to be able to actively keep polling as much as you can. Otherwise, you'll have the experience where you're playing the game and then sometimes the buttons don't work, which is a pretty unpleasant experience. We also found that delay didn't act really well with Bluetooth as well on here. So here's what a spin loop looks like. So the things to know looking at this code is that now is the current time. And so at the top of the main loop in Arduino, I say now equals millis, and that's the current time in milliseconds. So if the current time, the difference between the current time and when I last blinked was greater than this icon's flash interval, which I think is set to about 500 milliseconds, then I'm going to tell the game to blink. The game may choose not to blink and not bother implementing that, in which case nothing will happen. But if it's a game that wants to blink, it gets the opportunity. I then go and poll all the buttons, and I have this debouncer thing, which means on this game what the debouncer does is that it does a couple of things. It'll recognize if the button has been held down for enough time to register once, but it also has a repeat function. So you know how on a keyboard, if you hold down the key, it'll press once, and then after a while it'll go, whoa, okay, I guess they want to do this a lot, and so they'll start in repeat mode. So that whole debounce takes care of that. So, and then the thing is, once we've processed the buttons, we then go, and if the time since the last updater is greater than milliseconds per frame, which is about 60 milliseconds, then we go and tell the game to update. The other thing, and I want to thank Charles, who went before me, for talking about lookup tables, because we pre-calculate everything for this as much as possible, as Charles said. So what you want to do is, floating point is slow. You want to try to help that animation out as much as possible by not making it do floating point, just basically as much as possible you should be pre-calculating things. And so we pre-calculate the points for when we draw the lander. At each rotation, it has 16 different rotational positions, and we have those pre-calculated, so I'm not doing sines and cosines and things like that. We store the grayscale images and bitmaps in PROGMEM, and we have two kinds of things. So for the Commander game, I had a moon shape, a beautiful grayscale image of the moon. Takes a lot of memory, but it fits in PROGMEM, it's fine. And then for the bitmap of the lander that you see when you first turn it on, that's just a black and white bitmap that, of course, you can tell the TFT libraries to display in whatever color you choose. An alternative way, which a lot of the samples give you, is to show you storing bitmaps on an SD card. An SD card is a good solution if you've got enormous bitmaps, but if you're trying to distribute a badge, it's got a couple of drawbacks. One drawback is that if you lose your SD card, suddenly your badge doesn't work, or it doesn't display some of your bitmaps, and that would be sad. The other problem with it is that as a badge maker, you have to flash the SD cards as well as the badges. And so then you've got a problem where you've got a logistics problem. You're probably paying someone to get all of the data onto the SD cards, but you're also, at the same time, going to need to get the rest of the badge flashed and then make sure that everything works together. So logistically, it's a lot more complex to use a separate SD card. Okay. So let's talk about the interface with the hardware a bit. So most of these buttons, so this is how we define the interface with the hardware. And so the app, the shell that I wrote uses these ones. So we're using SPI to communicate with the display, and that's a pretty standard TFT display thing. The LEDs, we define, these are output GPIO pins. The buttons, we define the buttons here as well. We also define the GPIO and the SCL SDA port, pins for the shitty add-on. The software that we wrote here doesn't actually use the shitty add-on except to provide power to it. So we didn't do the communication with that. Another thing that's worth noticing here is that we monitor the battery level, and so there's a pin that's used for doing that. People who are more familiar with the ESP32 might notice that we're using pins 36 and 39 as inputs, and that was a problem. So after we'd built the badge and we got the prototype back, we thought, we really should do something to make this more interesting. So I looked up the specs, and hey, ESP32 has a Hall effect sensor. And what that means is you can go and put a magnet near the processor and detect that there's a magnet there. And so that sounded really cool. So I wrote this piece of software I wrote this function that will go and read the Hall effect sensor. And there's two things to notice about this. The first thing is when you go and look online, people will be saying, oh, that Hall effect sensor, it is not reliable. It gives me random numbers. It doesn't seem to work. But it turns out if you average it over about 1,000 readings, which is pretty quick. I know it seems like a big number, but if you average it over 1,000, it's actually fine. It's very stable. You just need to sample it enough. The other problem was that when we first wrote this code, and it didn't have those pin modes input lines there, it would cause two of the buttons to go haywire, and suddenly they would start firing randomly. So I went and read the code, and this is the great thing about basing your development on open source code, is that I realized that what the ESP32 code was doing was setting those pins to being analog so it could do the Hall read. So what I'm doing is setting them back to being regular digital input pins afterwards. And like that, it works. Now, I suspect most people who use the badge never figured out how to do that. So that's how it goes. I've got a hint on the last slide about how to actually make that work. So managing the display. We're using vector graphics, not raster, as I said. So what that means we're doing is we're using those TFT commands to call things like draw circle, draw filled triangle, draw lines, etc. So if you try to clear the screen each time around the loop, then what happens is you get this annoying flicker, and it just looks terrible. Nobody wants to see that. So what you do instead is, what I'm doing is I redraw the previous artifacts in whatever my background color is at the time. So that way, it looks pretty clean. And the experience from the user perspective is they cannot see those redraws. What they see is it looks like the lander moves smoothly across the screen, and the scrolling side to side and up and down just seems to work. So, it's very fortunate like that. So here's what we do in Update is Complete for the Lunar Lander game. We run our physics engine one step, telling it the current time, and it applies gravity to the lander. It applies thrust in either up or maybe down if you want to crash quickly. Get it over with. So it runs the physics engine, it redraws the screen, and it updates the heads-up display text on the screen. And then it returns true if you've won or you've lost or you quit. So let's talk a bit about scrolling. Now, the world is much larger than the screen. So what I want to do, and this is pretty common for these arcade-style games, is that the lander or the player stays in the middle of the screen, more or less. In this case, the lander stays exactly horizontally in the middle of the screen. It can move up and down a little bit because I don't scroll the mountains up beyond that 0 point. So the world wraps around horizontally. You don't notice when you're playing because you tend not to notice. If you're really looking for it, you can tell that I'm wrapping it. The sky above the ground also wraps vertically once you're above the mountains. So what you can do is decide, I want to see how high I can fly. And so you just blast it, go straight up, and it keeps scrolling. And after a while, it's scrolling, but it's not usually very obvious to people. So here's a picture of what this looks like and why the screen translation is a little complicated. So when I'm in the world coordinates, it's very convenient to have the ground be at 0. So I want to have the lower left-hand corner is where 0, 0 is in the world coordinates. And that's nice because gravity works the way you'd expect it to in the physics engine, and it means that it's obvious when I should stop scrolling down. When I get to 0, I stop scrolling down. On the other hand, the screen itself wants 0 to be in the top left. And so you can see here the pink rectangle is the actual camera, the world view that you're looking at. So you're looking through this little camera. Right. Okay, so, and so then the camera the camera gets scrolled left, down, up and right, etc. We also can zoom it. Now, when I started porting this to the Hackaday badge, which the port is not finished, because moving from vector graphics to raster graphics is not trivial, it turns out. When I started porting that, I decided that the zooming would be too complicated because I would probably need too many sprites. But here's how there's some macros. You're not expected to learn these macros, but you know, I use macros to convert from world coordinates to screen coordinates when I go to print. So the physics engine and all of the other things there for this game are in world coordinates, and then I just convert them back to screen when I go to display it. Color maps. Now, you know, on the Hackaday badge, it has this palette, and you can do interesting effects by shifting the palette. For this game, it's because of the way the graphics are working, what I'm doing instead is I'm giving a color map to each app that comes from the settings. And so I define what the background color looks like, which by default is black, etc. And so that's the default color map. And I just commented there with the colors so that I could remember what the defaults look like while I was doing that. But there are different color maps possible on this badge, and that lets you add a little bit of interest without a lot of code, actually. That was pretty easy. So let me talk a little bit about Bluetooth. So Bluetooth on the ESP32 works great, but it does take a lot of memory. And so what that happened is that when I compiled it for the first time running Bluetooth as well, it didn't fit. I couldn't load it onto the Arduino, using the Arduino IDE. I couldn't fit my app on the thing. So what I did was I looked around and realised that the right way to do it is to edit boards.txt. And so you can see the diff there. I'm actually using the Feather ESP32 as my fake board here. I could have created a new one, but it was easier to just reuse it and add some more stuff. So I added the default partition scheme for the ESP32, and then I added this new one, which was Huge App, which is predefined somewhere. And what that gives you is 3 meg of size for uploading instead of 1.2 meg. I'm sitting at about 1.4 meg, so I'm not that much over, but it was just enough that it wasn't going to be a happy thing. So that's a little tricky to find that. It's worth being aware of it. If you're writing one of these games and you need a bit more memory, that's how you get it. So in the Arduino settings, what you'll see is that I'm using the board is the ESP32 Feather, and the partition scheme is that one that we just defined. When I'm shipping it, I set with core debug level to none. I also use this tool, the ESP exception decoder, which is open source. It's available on GitHub, and it's highly recommended if you're doing any ESP work, because you'll find that it really helps if it crashes. And yes, I have crashed the ESP32 multiple times. As a software engineer, you know you spend most of your time looking at code that's broken, and this helps. Okay, so the other thing I noticed is that when I was running Bluetooth to scan, so let me take a step back and talk about how the Friends app works. So what it does is if you enable Bluetooth, passively it broadcasts your score for the Lunar Lander game to anyone who's around. So it'll send these little messages that say, hey, no full name, 256, or I think it was 1735 or something was my score, not that I'm counting. And so anybody who's around can then turn on Scan for Friends on that Friends app and find people around who may have also been playing the game. And they can get their scores, and their scores show up on the leaderboard that's on that Friends app. Now, the problem I had when we started doing this was that the badge would just lock up while scanning. And normally what happens if the badge is just turned on, I'll just turn this on, is that there's this little idle loop thing that runs these LEDs here. See the LEDs on the tail, and they just and it's kind of a comforting thing to know that the badge is still working. That stopped when I would turn the, when I would be doing Bluetooth scanning. And so if you're used to seeing those comforting lights flashing, you would decide that maybe the badge was dead and you'd turn it off. To get around that, what I was doing is running an idle loop on the second core of the ESP32. Arduino uses CPU 1, but that means the CPU 0 on the ESP32 typically is sitting there doing absolutely nothing. So what I'm doing is I run the idle task on there, and that keeps the those lights on while I'm doing scanning for Bluetooth. Okay. And then we're actually almost to the end of the really technical part of this. So the serial port. Now, when I gave this to one of the Kickstarter backers, one of the first people who received this badge said to me, "I don't see how to change my name. It looks like, you know, I can see that on your examples, you don't have badge number, some obfuscated version of the MAC address of the ESP32. And I'm like, yeah, that's right, I don't actually have that. And so, you know, it took a while for people to realize that actually you can use that serial port for a couple of other things. So while developing, of course, you use it for debugging, you print things out, you look at it and say, well, I see why that's not working. You can also print things out, do printfs to the serial port in order to slow things down so you can see what's going on if your animation is looking a bit janky and you're not sure what's going on. But you can change your name. So you can see the example there. If you connect it up to a serial, to some kind of serial device, like on the Mac you use screen to dev.tdy, and that will vary a little bit, so you might take a little while to figure out which one it's connected to. You can use PuTTY, you can use whatever, it's a VT100 is what the serial port on this thing, on an ESP32 looks like. VT100's being old technology even when I started in tech. So you can change your name. You can also have a serial version of the game. And so I did this for the Commander game. And so you can see on the right there that it says, you know, the command module is really important. And you're like, oh yeah, I know. And it says, okay, you see the moon, you see the command module orbiting the moon. The lander separates from the command module. It lands on the lunar surface. And then if you start pressing buttons because you're annoyed about this and you're kind of done, okay, this is really boring, this game, it starts popping up messages. Okay, and I think I'm about out of time, but you can see here, this was my hint for how the Hall effect sensor was supposed to work. So, these are the libraries that I used. These slides will be available later, I think. In any case, I'll leave this up for long enough that you can go and look at the recording later. A few more, I think I covered all of this. Play testing is really important for any game. And using Git is important so you can be brave about refactoring. It's very valuable to have a community. I lent heavily on the Badge Life community for getting feedback on this. And you know, the Hackaday community, the Badge Life communities are really awesome for helping with this. The code, as I said, is on GitHub. I have, there's some good resources here for converting bitmaps and so on. And finally, thank you to Badge Life communities, to DEF CON, the Kickstarter backers who supported developing this, our first badge. It's a huge risk putting your money behind a badge from somebody who's never delivered one before. My family and Rowan, who's sitting back there, who did the hardware design and challenged me to really improve the code by relentlessly play testing. Okay, thank you very much.